More interesting than a plane mirror, but still something we can do at this level, is what's called a spherical mirror. So if you imagine one of these shiny Christmas ornaments, like is shown here, where the inside is mirrored, imagine you cut a little circular segment out of that, something about the size of a quarter, and hold it in your hand. Now you have a spherical mirror because it was cut from a sphere, and where the inside is shiny, you'd have a concave spherical mirror. If the outside had not been painted, if that were shiny, you could use the outside as a convex spherical mirror. And there's basically two things we need to know about the mirror. One is it convex or concave? The inside here concave, the outside convex. Uh, the other thing is what's called the radius of curvature. This is not the radius of the circle that we cut out of this, the radius of the quarter. It's the radius of this ball, the sphere that the mirror was cut from. So the radius of the ornament here is probably 2 or 3 centimeters, something like that. So let's say we have a concave mirror with a radius of curvature capital R, and we shine parallel light on it. We know that light spreads out in all directions from a point source. So how do we end up with parallel light? First, imagine we have a piece of paper close to this light. We've got light, if I drew this a little better, maybe we'd have light from the top of the bulb hitting the paper and light from the side of the bulb hitting the paper. So those two rays were initially 90 degrees apart and they both hit the paper, if I bring it close enough. On the other hand, what if I take this piece of paper very, very far away? The rays that hit the top and the bottom of the paper are almost in the same direction. There's a very small angle between them. As I move the source further and further away, the light rays that hit the paper become closer and closer to parallel. So in the limit that we move the light source to infinity, the light rays are parallel all over the paper. Now, of course, we're not going to be infinitely far away from something, but like everything else in physics, there's a scale that gives us an idea of the importance of something. And the scale here would be how big is this piece of paper compared to your distance to this point source. That tells us where we would get parallel light. For example, the sun is almost always good enough as parallel light. We can consider the light from it to be parallel in almost every case. Now that we have a way to get parallel light, what happens if we shine it at this concave mirror? Well, what we notice, here's our radius of curvature. If you imagine filling this out and making the sphere, the center would be right here, and our radius of curvature is R. We notice a couple of things. The normals, which are all along the surface, all point to the center of the Christmas ornament. That's not a surprise because we know a radius vector from anywhere on this would point towards the center, and that's what the normal is. It's perpendicular to the surface. So the light rays from all these different parts of the mirror land at the same place. This is a little bit of an approximation, but for right now, let's say it's true. The light rays all land at the same place, and it's half of the radius of curvature from the mirror. So it's halfway from this end of the mirror to the center of the ball that this was cut from. The point where all this parallel light comes together is called the focus. And the distance from this to the mirror, this way, is the focal length. And this is a fixed property of the mirror. So once we know it, it's never going to change. So we could also say the focal length is equal to r over 2, where r is our radius of curvature. That could be, we could stamp that on the mirror if we wanted to, or engrave it or whatever. So there's our focal length. This is defined as positive for a concave mirror. We'll next look at a convex mirror, like the one below, and there we would define the focal length as negative.